Okay, yes, welcome back, everybody. So this will be the second lecture on stochastic thermodynamics. I've talked a lot about the first law, about the concept of work yesterday. A thermodynamic framework would not be complete without speaking about entropy in this context. And this will be the major first theme during today's lecture, and then I would like to talk about non-equilibrium steady states, which are a particular class of non-equilibrium states, which are perhaps arguably the most simplest one, beyond equilibrium and beyond linear response. Okay, so who was not here yesterday? Okay, so I can be very brief here in this recapitulation. So we're still looking at mechanically driven systems. I have introduced this non-linear dynamics yesterday. We will today mostly speak about a particle driven across such a periodic potential. I will show you experiments on that. In this non-linear dynamics, it's overdamped. U is the mobility. The total force can arise from a gradient of the potential or some non-conservative part. Both contributions can depend on an external control parameter, lambda of tau. There is some noise here, and the strength of the noise is related to the mobility by the usual Einstein relation. I will call this the Einstein relation and not the fluctuation dissipation theorem, because we will speak about the fluctuation dissipation theorem at length later. Equivalent to such a non-linear dynamics, which focuses on the individual trajectories, is a description of the whole ensemble, which is given by the Fokker-Planck equation. So P of x and tau is the probability to find a particle at time tau at position x. That's the probability. It can be written as the divergence of the current. And the current is given as a deterministic piece, given by the mobility times the force times the probability, and it has a diffusive piece arising from gradients in the probability distribution. Okay, now let me come to my main concept, and that's the concept of stochastic entropy. So I've just introduced this Fokker-Planck equation. This Fokker-Planck equation needs an initial distribution. And suppose now you have this Fokker-Planck equation with a given initial distribution, we can assume that we have solved this Fokker-Planck equation. And then this capital S quantity is a generalization of the well-known Gibbs entropy minus sum over P n and P to a dynamic situation where this probability distribution is highly different. So this is nothing new, and presumably 90% of the physicists would accept this as a reasonable non-equilibrium ensemble definition of entropy non-equilibrium. Okay, but if you now look at this object very carefully, you see that you can write it as a non-equilibrium average over a quantity little s of tau, which I will define here. So this is a stochastic quantity. It depends on the trajectory, and what you do is the following procedure. You first solve the Fokker-Planck equation. Once you have solved the Fokker-Planck equation, you take as the first argument in this Fokker-Planck equation, you take a specific trajectory from this ensemble, which is described by the Fokker-Planck equation. Okay? And this is a well-defined object, and I call this object stochastic entropy. Why I call it stochastic entropy, you'll see in a minute. So far, and this is the single most important concept of today's lecture, so I would like to have everybody at least an understanding how you get to this object. So perhaps let me write down what this would mean in equilibrium. In equilibrium, we have a probability distribution is not time dependent, and it's given by e to the minus energy, or let's say potential V of x minus the energy as a normalization divided by kb. Okay, that's it, kb to 1 divided by 2. So that's the distribution. we also in equilibrium have, let's say we have some potential, we have some fluctuating trajectory, x of tau, and when we now look at s of tau, we just have to look at minus ln of this object. Well, this is nothing but v of x minus a constant divided by t. Okay, or rewritten, this is F free energy is v of x minus, okay, let me write it more clearly, x of tau. This is the fluctuating trajectory in equilibrium, little s. Okay, so with this definition, you get your familiar thermodynamic relation now on the basis of a single trajectory in equilibrium. Okay? And now we can do that also for non-equilibrium, so here is the definition. Any questions to that definition? Yes, please.
When you think of entropy, you usually think of number of ways of doing something. So when you say a single trajectory, what do you mean by it? I don't understand.
Okay. You're asking not about this definition, you're asking about the meaning of this object. I will tell you the meaning of this object in a minute. I just want you to accept this definition at the moment. Okay. So once we have defined this object, we can look at its equation of motion. So the time derivative of this object has one contribution from here. So whenever this p is explicitly time dependent, we have to look at that part. And here we have to look at the implicit time derivative. So this is a dp dx. But due to the Fokker-Planck equation, we can write dp dx. We can express dp dx by the current and this piece. So we do that here, and we get this time evolution of this object. Now this part we have identified yesterday as the increment of the entropy of the surrounding medium. This was the heat, or Q dot. Okay, so if this is the entropy change of the medium, and this is the entropy change of the system, this whole bracket has to be the entropy change of the universe. And it's now the entropy change of the universe along the single fluctuating trajectory. And if I integrate this up, I get this relation for finite changes. Okay, so why is this, in my opinion, why is this a good concept, and why can I call that entropy? I'll show you two pieces of evidence.
What is M?
Oh yeah, sub M is the environment, the medium. That's the surroundings. And yesterday we had defined the total force times displacement, that's the frictional heat that is dissipated in the environment. The environment has a fixed temperature, and therefore if I divide this heat by temperature, which is hidden in this diffusion constant, mind you this is mu times T, the mu cancels, then this is heat divided by T, and that's the increment of the entropy.
J is the probability current, right?
Excuse me?
J is the probability current, J is the
J is the probability current, yes. J is the probability current. Just whatever is behind this. Okay, so first piece of evidence. Yesterday I've proven this general relation. General relation which holds for any normalized function of the endpoint. So let's now choose perhaps arguably the most natural normalized function of the endpoint. That's the probability distribution by itself. So if I choose for this P1 function of the endpoint the solution of the Fokker-Planck equation, well, this is e to the minus s of t. ln P naught is the entropy of the initial point along this trajectory. So this is the total entropy change of the system. This is the entropy change of the medium, including the minus signs. So this exponent, after this choice, becomes the total entropy change of the universe. Since I have proven this box, I have now a statement that e to the minus total entropy change averaged in this non-equilibrium ensemble is always 1, from which you, by Jensen, you get this second law-like statement. So with these definitions, the average of the entropy change of the universe is always positive. This is what I call an integral fluctuation theory for the total entropy production, and it's quite general. It holds for an arbitrary initial state. I did not specify any equilibrium state, or I didn't have to for the initial state. It holds for an arbitrary timing. The potential can be time-dependent, the non-conservative force can be time-dependent, and it holds for an arbitrary length of trajectories over which I integrate up this entropy change. So I think it's a really nice kind of universal result, which you get if you accept this definition. Okay. Good. This is particularly a good place to point out the relation of this theorem to other relations in the literature. It turns out that they are all actually special cases of this very general relation. So it depends on what you choose as this function. If as this free function you choose the probability distribution by itself, you get what we just discussed. If you are in a situation where you start initially in equilibrium, and where you have no non-conservative forces, if you then choose for this P1, the Boltzmann distribution, at the end point you get the Jarzynski relation, as I've told you already yesterday. Now suppose in the same situation you choose the Boltzmann distribution, which corresponds to the initial value of the control parameter. You're free to do that, to choose that as this function. Then you get a relation which looks a little bit like the Jarzynski relation. You get e to the minus some slightly differently defined work is 1. And that's the Bochkov-Kusolev relation, which has been around for 30 years when Jarzynski wrote his paper, not knowing about it. Then later some people have claimed that the Jarzynski relation is just the Bochkov-Kusolev relation. That's nonsense. There is a certain difference, but it falls also into this class of very general relations. And you can also choose, any function of the endpoint times the probability distribution, the equilibrium distribution at the endpoint, and then you get something which, to my knowledge, first occurred in another paper of Crookes. This is not what yesterday was called the Crookes relation, but it occurred for the first time. Also in a Crookes paper, and I had this table some 3 years ago, and then I would usually say that if you want to become famous, you just choose your own P1 function, publish it, and call it your own integral fluctuation theorem. This was 3 years ago, and presumably now this game is quite well understood. Leon?
Yeah, I forgot. P0, that's the initial distribution?
That's the initial distribution with which you start, yes.
And somehow these statements... These statements do not depend on what you take that distribution to be?
This statement does not. It holds for an arbitrary P0. For Jarzynski and Kusolev, you have to start initially in equilibrium. Okay. Only then these relations. Likewise for this.
But the final state doesn't have to be equilibrium.
No. The final state is whatever it is.
Right.
This is not the key point. This is not the final distribution. This can be any function. If you choose the P function to be the final distribution, you get what we just discussed.
Oh, I see. Okay.
If you choose this thing, you get Jarzynski. If you choose this thing, you get Bochkov-Kusolev. All for the same system.
Well, P1 is not a final state, but when you're choosing it in the third line to be P1 equals to P equilibrium, you're not choosing the final state to be equilibrium.
No. It's a mathematical device.
Okay.
It's a black box. You take sine x for a periodic system and you get something. Jeff.
You've done this in the context of modular systems.
Yes.
Some of these relations hold for other dynamics.
Yes.
Does the general fluctuation theory hold for more general fluctuation?
I will come to that tomorrow. Yes. It holds for any kind of Langevin equation. It holds even for master equations that we'll talk about tomorrow. Yes.
Yeah, so in your previous slide, could you give a little bit more information or explanation about the David model?
Well, you just do it.
Yeah.
well, here is a time dependence, this is this part, here is a x dependence, these are these two parts, and then you have to do by chain rule. And for the dp dx, you just use the definition J is mu times f times b minus d dxb. Okay, so this was the relation of these various integral fluctuation theorems, and now I would like to talk for the rest of today's lecture about non-equilibrium steady states, but of course I will talk about entropy in this context here as well. So we now have a time-independent potential and a time-independent conservative force. And the harmonic oscillator, as Danny would call it, or the Ising model, as you could call it, for such a nest is actually, in my opinion, really this is, at least on the longer run level. So, after a certain time, with whatever initial distribution you start, a stationary distribution becomes established, which of course is not the Boltzmann distribution. And it's not the Boltzmann distribution because these nest states are different from equilibrium states by the very important fact that detail balance is broken. You know, detail balance means the probability to be in state 1 and to jump to state 2 in time t is the same as the probability to be in state 2 and jump from 2 to 1. So if you have an equality there, this is an equilibrium state. If you have a non-equality there, it's a nest state. And in such a nest state, there is a current, and I call this current sometimes the mean global velocity. I should call it the global velocity actually. It's the average over what is sensibly called the mean local velocity. That's an important quantity in the following slides. So nu sub s is the average value of the velocity given that you are at position x. That's the definition. You can also write it as the current divided by the probability to be at x. Or you can write the current as the probability to be at x times that mean velocity at this point. And if you use the Fokker-Planck equation, you can also write it in this way. Okay.
Well, can you say, I mean, it seems like the right-hand side is still divergent of a current, right? So if you want to get steady state, where...
I'm using these definitions only in steady state.
Right, so then the left-hand side of your Fokker-Planck equation is 0, right? So dp is 0.
Yes, okay, so let's do that here. So we have 0 is minus dx j, and j is mu f p minus mu t dx p, and we divide by p, then we have mu is mu f minus mu t dx ln p, and this is what I call phi. Okay? That answer your question?
So almost. I mean, so that's what I was getting to. So I mean, the current is not 0, but the derivative is 0. So
dxj is 0. Yeah. I mean, j is constant in 1.
So current is non-zero, but divergence is non-zero. Is 0.
Divergence is 0. Yes. Current is non-zero, and in 1D the current is independent of x. In 2D or higher dimensions, the stationary current would be a function of x, but its divergence would still be 0 because we're in a non-equilibrium steady state.
You just somehow the current is growing and will stay? Current is a linear function of x?
No.
Yes, the velocity is.
The current is a constant. Would that be a linear function of x?
Oh no.
It's not a linear function of x. It's only a linear function of x if you use your quadratic form. I'll show you examples. No, I will not today. Okay. So, what can you now do in such a non-equilibrium steady state? The point is that we have stronger results on these non-equilibrium steady states than for the cases where we have time-dependent variations of parameters. And presumably one of the most beautiful results in such steady states is this boxed fluctuation theorem, which gives you the probability to find trajectories with a negative total entropy production is constrained by this relation. So this is the original fluctuation theorem. It was found 1993 in simulations of two-dimensional shear fluids by Evans, Cohen, and Morris. It was then proven quite some heavy mathematics by Galavotti and Cohen, assuming chaotic dynamics and also of A systems. And then Kulchan had the insight that you can do the same thing using stochastic dynamics, and that was later generalized by Lebowitz and Spohn. In all these papers, this is an asymptotic statement in the long time limit. If you accept my definition of entropy, you get this box for finite time, for any finite time, which I think is another indication why this concept of system entropy, the way we have defined it 2 slides ago, makes a lot of sense. You get now this nice result also for finite times. When this result showed up for the first time, people tried, or people sold it with this notion of the violation of the second law, or transient violations of the second law, but I think this is not very, this is not a description I would really endorse. The point, of course, is that for that to be true, you have to have trajectories with total negative entropy production. But I mean, the second law was never meant to hold on the level of the second trajectory.
This is any kind of dimension statement.
No, this is no. Wait, this is a statement in the non-equilibrium steady state. We're now in the non-equilibrium steady state. For the rest of this talk, we are in the non-equilibrium state. So what this box means is, suppose someone gives you the right-hand side of this probability distribution, then this box gives you the left-hand side. So it's essentially half of the information of the distribution. It's a constraint on the distribution, but it does not fix the distribution. And I will now show you here are the results, how such probability distributions really look like for this situation where we have this particle driven across a periodic potential. So this is this probability distribution for short times. After 2 seconds, you get basically these 2 peaks. The peak at 0 means the particle hasn't moved, hence nothing has been dissipated. This peak means the particle has overcome the barrier 1 time. After 20 seconds, it looks like this. And in the lower panel, this is for a different force. This is right at the critical force, where this non-conservative force just cancels the strongest slope of the potential. This is beyond the critical force. The point, why I'm showing you this, the point is that I would like to raise your awareness that such probability functions can really look complicated. I mean, this is anything but a Gaussian distribution. Still, the piece here at negative values has to fulfill this box. And we have checked this. Of course, there is some statistics, but at least for this situation, it works quite well. Okay, so this is the fluctuation theorem. Now, I mean, there is not much hope that you can, for more complicated systems, calculate this analytically, and also, this looks very, very non-universal. So a more universal question you can ask is, how does this probability distribution look in the long time limit? And that takes us to this large deviation form. So the idea is here that we look at the system for a long time. We define a scaled entropy production rate. So delta Sm is the entropy production in the medium, but for this type of system, the entropy production in the system is bounded anyway, so it doesn't make a big difference here, the sub m. This is the average entropy production. So sigma to 1 would be events where you just have the average entropy production. And then the statement is that in the long time limit, this probability distribution obeys this large deviation form, which we also have seen yesterday. So these deviations from the mean are exponentially small for long times, and this prefactor, this prefunction here, is the rate function, and the fluctuation theorem constrains the form of this rate function. Okay, so this rate function has this kind of symmetry, and you can calculate it for this situation. And what you then find are these curves. This is now for different forces. In the linear response regime, you have a Gaussian distribution, which means a parabola for this rate function. Beyond that, you get deviations from a parabola, and it turns out that you even can have singularities or kink-like singularities here at zero in a certain limit of strong force. You can actually map this model where this particle is driven across this potential to an asymmetric random walk. And the nice thing about an asymmetric random walk is that you can calculate this large deviation function exactly. And here are comparisons between what we call here the continuous calculation and the asymmetric random walk. And for very small forces, it works quite nicely. Here it also works quite nicely. But here, for very strong forces, where you can no longer have this simple promise picture, you get deviations here for large entropy production rates. So here is now a research project. Are there universality classes for these rate functions for different systems? Beyond this constraint, how can these functions look like? We have found three systems where we get singularities, or where in certain limits at this 0 point. This is something we do not yet fully understand, so whoever is interested in that, I would encourage you to think about, are there something like universality classes for such rate functions? If we look for universality in non-equilibrium systems beyond phase transitions, I think that would be one question one could try to pursue. Okay, let me briefly show you how you prove that. The basic idea is, in the stochastic context, again looking at backward and forward trajectories. So here is again the definition of the total entropy production. And we now look at any function of this total entropy production in the non-equilibrium ensemble. So we have to sum over all paths. That's now the steady state distribution. That's the propagation. We sum over all paths. We now use the symmetry expressed by the backward path. Whether we sum over forward paths. Oh, I just see this N naught should be X naught. I'm sorry. N naught should be X naught. Whether we sum over a forward path or over a backward path doesn't matter. We change these dummy variables, and we get a non-equilibrium average of the original ensemble over this quantity. And if you now take for G the characteristic function, you get this class. So this proof within the stochastic dynamics is rather simple. It fits on one page. We should compare that to the Galavotti-Cohen proof using chaotic dynamics to appreciate how simple that is. Okay. Any questions on the... Yes, please.
So the large deviation, if you please go back one slide. Yes, is there a clue of how the curvature is p-factor looks like?
Sorry,
is the p-factor in the large deviation, like before the exponential, is that order 1? Is that 1?
Well, that's normalized with respect to the average rate, right? If you choose sigma to be 0, no, sigma to be 1, sigma 1 means probability to observe the average rate, then this h function is 0. So the prefactor is p of average. That's how it's normalized. Okay. I would now like to come to the fluctuation dissipation theorem, and I think I'll first challenge you on your knowledge about the usual FDT so that you can appreciate what has been done here. And let me phrase this. Who is really a hard condensed matter person here? More or less? Solid state people? We do have solid state, correct? Okay, good. So suppose you have some magnet and you have some magnetic field, and you want to understand in equilibrium how does a spin at position I at time t2 on average react to a magnetic field which you have applied at point J at some earlier time t1. What's that? Okay. That's the response function, yes. And it is in equilibrium. It's a correlation function. So in equilibrium, this is the correlation function Si at times t2 Sj at times t1. And you have to differentiate with respect to the earlier time. Okay. So this is the FDT. This is the FDT in equilibrium. So what's important about this? I can express the response of any observable by a correlation of this observable with some other observable taken at earlier time. What is this other observable which I have to take at earlier time? This other observable is the observable which is conjugate with respect to the perturbation in the energy. So H times S, that's the shift in energy when you apply this perturbation. That's the logic behind the FDT in equilibrium. Okay, and now we want to do similar things for this Longemer system in non-equilibrium. That's the background. So this we had. So now it's common knowledge that in non-equilibrium steady state, the fluctuation dissipation theorem doesn't hold. What's not known is what is replacing the fluctuation dissipation theorem for non-equilibrium steady states. And this is something we have looked at more recently. So I can ask, even in equilibrium here, I can ask the question, so in equilibrium there is no non-conservative force, there's just a time-independent potential. And then I can ask the question, how does the velocity at some later time t change if I apply a force at some earlier time tau? And in equilibrium, it turns out to be expressible by this correlation function. So we have the t over there as well. The conjugate variable with respect to, in energy with respect to such a perturbation in the force times displacement is the conjugate variable. So that's why you get the x here at the earlier time, and the dot here is just pulling in this time derivative. So that's exactly the same structure. Now suppose we are looking not at an equilibrium situation, but at a situation where we have a certain force. We now can still ask the question, suppose we add an additional force pulse at some earlier time, how does the velocity in this non-equilibrium steady state respond to that force at the later time? So this quantity is still well defined, but we now take this average not in equilibrium, but in the NES. And a calculation which I can sketch if you want, shows the result. The result is that this response is still given by the correlation function, but now taken in non-equilibrium, minus some additional term. And this additional term involves the observable I'm looking for, and at the earlier time an observable which turns out to be the mean velocity at the earlier position. Okay? I mean, this is nothing which you can see. This is a two-page calculation which I can sketch once we're through that. But this was our result. Why did we like this result? Well,
this is the mean velocity now. This is the.
I have defined this nu is the phase space function. Nu of x is mobility times the force of x minus this thing here at this taken in this non-equilibrium steady state. So nu is a function of x. Okay, and for this operation, you just have to use as the argument the x at the earlier time. And this is a correlation function which you can easily extract from a simulation or an experiment. This is just what you have to do. Okay?
Okay, but this is not the mean value. This is for a given configuration.
The new S. I don't know what to mean with the mean value.
No, you said some seconds before the mean velocity.
The mean local velocity. I should have. Sorry. This was my mistake. Yeah, thank you for pointing out. The mean local velocity. It's this function. Okay, once you have that, it's trivial to show that if you define a renormalized velocity, where you take the actual velocity minus the local mean velocity at this position, that you then find that this velocity responds to a force at some earlier time exactly as this velocity responds in equilibrium. So you now get back, and that's why we have called this restoration, you get back the structure of the FDT now for a non-equilibrium quantity. Okay, so this looks a little bit formal. I'll try to explain the physics behind it. What is the physics behind the FDT in equilibrium? The physics behind it is Onsager's idea or insight that two situations are comparable in equilibrium. If you look at how a fluctuation decays in equilibrium, it doesn't matter whether this fluctuation has been generated by an external force or whether it has been generated by thermal fluctuations. This result tells you that for a fluctuation in a non-equilibrium steady state, taken with respect to the average mean velocity, it doesn't matter whether such a fluctuation has been caused by an additional external force or whether it has occurred spontaneously. So that's kind of translating Onsager's idea to non-equilibrium steady states. That's the physics behind it. Yes, please.
What is the meaning of temperature?
The meaning of temperature here is exactly like here. Remember when I use the Langevin equation, I insist on having the zeta-zeta correlation by 2 mu kBT. That's why temperature is in the game. Also, if you look at the Fokker-Planck, so I can use temperature even for these kind of non-equilibrium steady states because we're looking at the small system here, looking at this colloidal particle. It's still embedded in this aqueous solution. This aqueous solution has still room temperature. So this is what I tried to explain yesterday, that this whole theory applies to such systems where the environment still has a reasonable temperature. I mean, you can generalize this also to more general systems where you don't have temperature. But for these Langevin systems, as I've shown you yesterday, I mean, you can make this assumption even way beyond linear response.
But you're still assuming that your noise, that the functional form of the noise is not changed by the drive. So
yes, I'm still assuming that.
White noise, and if there's a different factor, you can scale that, you'll think of that, but it's still, it's basically behaving as an equilibrium, despite the fact that
Yes, and this is something you cannot prove theoretically. This is something which you have to check, for instance, experimentally or in simulation. So.
Well, it's not going to be holding in any arbitrary system.
That's true. That's why I try to state very clearly the rules of the games using this Langevin equation in non-equilibrium. Yes, Roman?
But isn't there some assumption about the driving has to be small? Because if you say the path still has to be equilibrium, you can't drive it so fast enough that you change the equilibrium of the path.
Yes, you can certainly drive it so fast that this Langevin description or this Fokker-Planck friction breaks down. That's just rephrasing what Uwe said.
Yeah, so it's still something like a linear response. Right?
No, I insist that this is beyond linear response.
So the system can be far from equilibrium while the bath is still at a well-defined temperature.
The system, the particle itself, is far from equilibrium. Yes, this distribution is very much non-Boltzmann-like, but still these results apply. You see, but the point is the following. Let's look at the strength of the force. So force 0, that's equilibrium. Force small, that's linear response. Finite force is Boltzmann equation still valid, beyond linear response, non-Gaussian work distribution. And if I now apply a little bit of an additional force, I'm exactly in the situation I'm describing here. I'm in a non-equilibrium steady state, but I apply a little bit of extra force. It's linear response with respect to this state, but it's of course not linear response with respect to equilibrium. That's the key point. You had a question?
So there is another way that you can go into non-equilibrium, which is set f to 0, but drive the potential. And do you expect a similar kind of fluctuation dissipation theorem in that case also?
Yes.
You do?
Yes. That's a very good question. You can also change. Essentially, you can change any parameter in this Fokker-Planck equation, and you get a similar structure. So let me tell you a little bit more after we have now discussed that where this has led to. So Gawecki in Lyon has shown more generally than based on this idea that if you have to go, you just go to a local co-moving frame and then you restore the equilibrium fluctuations in this moving frame. There are two papers, a long one on Chase.Mech and a new one in the archive, where he followed this idea and generalized it to general driven diffusive processes. But the basic physics behind it is what I tried to explain when I talked about this Onsager idea.
Now
Yes?
I'm confused.
Okay.
Coming back to Royce's lecture last week, if I just go into a co-moving frame, I'm messing with the nodes. That's basic. So that's why I'm confused. So I can certainly get rid of the, what you call the average mean velocity by going to co-moving frame, but then I'm mocking up my hitchcock.
Okay.
Right?
Yeah, that's different, right? I mean, what I was talking about before is going into the moving frame, and now that thing looks like equilibrium. This thing doesn't look like equilibrium.
Well, I think that was just the argument.
Okay.
No.
Okay.
The non-equilibrium steady state distribution is not the equilibrium.
Yes.
It's just this equation looks like it.
Okay. Good. Okay.
Looks like it.
So so I should point out that so you have this structure now, of course, again for n-coupled local systems, and then you just have to use this local mean velocity. Of course, then it becomes a function of all n coordinates. Okay.
I'm also getting my confused. The averages are over the non-equilibrium steady state distribution, right?
On the right-hand side, yes.
On the right-hand side,
Yes.
So I do this Galilean transformation. If I go into the co-moving form, this is now a different distribution, but it's still not the equilibrium distribution. Is that the statement?
Yes, and you see, you have to go to a locally co-moving frame. It's not a Galilei transformation. It's a local co-moving frame. And if I understood correctly, Gawecki's most recent claim is, and you have to look that up, it's a very mathematical paper, but his most recent claim is that in this locally co-moving frame, the fluctuations are not distinguishable from equilibrium fluctuations.
That's knowing a lot. That means you have to know what the local co-moving.
Yes, true. That's the price you pay.
That means knowing a heck of a lot about the non-equilibrium state.
Yeah, sure. That means knowing this function. But that's his statement. Okay.
useful is it?
It's not. I don't think it's particularly useful. I mean, even that is, even that is difficult to evaluate if you don't know this function.
Exactly. Yeah. You have to know a lot about this.
Yes.
Well, that's a funny local Galilei transformation.
Don't call it Galilei.
I know. Okay, so it's actually a perfect price, but that would make all these nest cases in some way locally equivalent to equilibrium. So
that's his claim. That's his claim in the appropriate co-moving frame. I mean, I have to understand. I have to admit that I seen that 4 weeks ago, and it's real mathematical physics. But I think, I mean, I see this basic idea in this whole approach. Yeah.
A totally different question. I mean, what are you doing here reminds me a lot of the kind of things people do in microfluidics experiments. So some particles are being pushed down channels, etc. Now you have these relationships. Does it allow you to say something about the background potential that you might not know? So let's say you have a colloidal particle that's driven in some potential that you don't know, and you'd like to find out something about this potential.
Okay.
I'm asking an inverse question.
Yes, I haven't thought about it, but certainly it means that if you look at response and correlation in that systems, that you can, I mean, that's rephrasing what you just said, that you might get information on this. But, this is still a two-and function. Yeah, but I think, we're not talking, as you see, since I don't explain myself clearly enough, we're now talking about the frontier of current research here. Okay. Why?
I think as far as, your comment about how quote useful it is, we should remind ourselves when FDG is used in equilibrium. So you would run the simulation, say, and you would check FDG as a way to say you are in equilibrium. So you look at this thing and you have no idea what to do because you don't know what the test is.
Yes.
So you can't really use it in that sense, for example.
Okay, now I will surprise you. I will show you a variant. I will show you a variant which might be useful. Okay, so what we have shown here is the x dot at time 2. Let me do a little bit of shorthand notation with respect to a force at time 1. That this is x dot 2. Take x dot 1 minus mu 1. And your criticism is that's not useful because you don't know that. Fair enough. Okay. This is also true. You can also write this as x dot 1 minus f at time 1. And that's useful. Oh, this is not on the slide. Okay. Okay. Okay, so my claim is this is true, and that's true as well. There's a factor of 1/2. That's crucial. That's crucial. Okay. And actually, there are many. Yeah, and now you can use linear combinations of that. So why is that nice? That's nice because you don't need to know the unknown phase space distribution. Okay, how do you prove these things? I can sketch now. Yes.
I guess I'd like to just make a comment. This is similar to something that's done in turbulence. And there, it's called the transformed Eulerian mean.
The transformed
Eulerian mean.
Yes. Yes. Yes.
And what you're doing is you're pulling out the motion that preserves the probability. And you're only looking at motion sort of transverse to the surface of the constant probability.
Yes.
Because V goes along the surface of the constant probability.
Yes. 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 I think that's Galensky's idea. Yes. And he explicitly uses this notion of Eulerian.
Yes.
Right.
And that's actually used. It's state-of-the-art technology in quantum physics.
Okay. Okay. So physicists to talk to climatologists. Good. So it's getting a little bit confusing. So let me continue and perhaps we pick up on this. Okay. Of course, I would like to show. It would be nice to have experimental data on that. We're not quite there yet, but we have checked or looked at an integrated version of this. So this again is this FDT in non-equilibrium with this extra term. Now suppose you integrate this over time from -infinity up to time t, then this is the total response, and that's the mobility in the presence of a force. If you integrate up this becomes the effective diffusion coefficient, and then this is just some extra term defined over there. And this is something which you can measure. So Beckinger's group, they have measured these three quantities independently. This question?
Yeah, where did the temperature go in the first one?
KBT is 1. Sorry. I'm sorry. So I should tell you one more piece of information. Suppose you have this particle in this periodic potential, no force in equilibrium. You can still define, even in the presence of this potential, you can define a diffusion coefficient, and that's a diffusion coefficient which would depend on the potential, and you still can ask for its mobility, i.e. applying in the linear response regime a small force, you can ask about the average change of the velocity, and then this mobility would still obey the Einstein relation. Right? So this is true, of course, also in the presence of the potential. But now suppose we have an additional force, then of course this is no longer true. And these quantities are defined here as parameters. They have measured these quantities, and the result is shown here. This is now for 5 different types of forces: mobility, diffusion coefficient, extra term. The white bar is the diffusion coefficient, the effective diffusion coefficient. The black bar is the effective mobility, and the gray bar is this extra term. And again, what you see is this extra term is 4 times as big as the mobility, which means we're way beyond linear response. And this is the linear response result, these new criteria. Way beyond linear response, still quite reasonable agreement here between the two bars, which is again a check whether this Langevin description is valid in that regime. Okay, so the strong enhancement of the diffusion coefficient as a function of force, and actually in particular at the critical force, that's well known. That's the phenomenon of giant diffusion discussed by Riemann and Kohlberg some time ago. I should also stress that such an additive correction term is very different from what people do in the glass business, where an effective temperature is introduced to restore the equilibrium form of the FDT. I mean, this is, as far as I understand, mostly a phenomenological procedure, and I'm deeply convinced that for these genuine non-equilibrium steady states, no aging, no waiting times, genuineness, such an additive correction is physically much more transparent, because I mean these are physically transparent functions. And I advertise very strongly to leave this concept of effective temperature for such nest states.
It's also very clear here that this additive term depends on the variable that you're looking at. It depends on the x.
You have to be careful.
Well, you get it. X is a set of variables, right?
Well, it's a function, and you have to take it at the earlier time. But of course, whether you look at x here or any other observable, you still have to correct with this function. So you still have this universality in the sense that it doesn't matter which operator you choose here. The conjugate variable is still doesn't depend on the choice of the observable whose response you're looking for.
It's true, but the whole integral that you add to that involves
I mean,
the extra.
yes, that involves the extra too, sure.
And the mu depends on not just the observed position of the observed variables, but all of them.
Yes, you have to observe all variables in a higher dimensional space. Yes. There was one more question. Yes.
How are you defining the mobility and the diffusivity in these Nonequilibrium study states, and what are they measuring in the experiment to compare the two numbers?
You define it. Okay. You define it. It's the time integral of this quantity. Okay. So it's you apply a little bit of force, and you look how the average velocity changes. That's just x. Okay. The diffusion coefficient is such that x of t minus x naught, x of t minus x naught minus average velocity times t squared goes like 2d effective times t. So you subtract the mean velocity, you look at fluctuations around that, and that's what you call the effective diffusion coefficient. Say it again, please. There is no T effective. That's my whole point. Forget about T effective. Yes, Vaz?
I was just going to comment that the trouble with T effective in general is that gives you the idea that another system with the same T effective, whatever it is, 37 substances, you bring it together and they will not exchange anything. That's unreasonable. In general.
Yes. Yeah, I
cannot do that.
Yes.
So in that sense, T effective is very misleading.
It also tends to depend on the observable, which makes it worse.
It also depends on the observable and the result.
Yes. And it may even depend on the time difference.
Yeah.
Yes. No, I fully agree. But I mean, there's this enormous literature on the effective temperature, and I think it's. But the the weights are shifting. You see more and more people using this idea now. That was another question. Yes.
Yeah, I'm not hugely familiar with the effective temperature, but I have seen these beautiful correlation or response plots with definitively different slopes in the driven regime. So I was wondering how your formulas and has anybody tried to actually use that to explain and understand this data?
You're referring to which kind of experiments?
The systems or the colloidal systems that are being sheared at constant rate? Not aging system, no.
Okay, so genuine nest. No, I mean what we are doing currently is we're using that for sheared suspensions of colloidal particles.
Yeah. Just
do numerical work. But of course, we will try to get these two separate contributions. I don't have the capacity to now try to also, or we haven't done it yet, try to check this effective temperature concept.
But it does explain the data, so the second linear regime and the.
Well, I don't know whether it explains the data. It's a good fit to the data.
It's a good fit to the data.
Yes, okay. I agree, but we want to understand physics.
So I have a question here. So in this system, you have a very small system connected to a thermal bath.
Yes.
And then I agree that you don't need a T effective and you can probably go this way. But the system where the T effective is invoked usually is that the whole system is so large. You don't have something of a thermal bath to connect it. You're looking at local temperature, some definition of local temperature that you can use. And usually it's used as the configurational entropy defines that T effective.
Okay.
So I don't see how you can generalize this to that case.
No, I can generalize this to arbitrary Langevin systems. I can generalize this, as I'll show or indicate tomorrow, to an arbitrary kind of stochastic dynamics. You get similar results. These are the two classes I can generalize.
Yeah, so it doesn't follow this. I mean, it was a rather hopeless attempt to have some sort of a definition of a local, configuration of entropy. That is really what's happening with P effective in the cases that you mentioned.
Yes.
And I don't see in your formalism how you can do that.
Well, I'm not claiming I could do it for a shared granular system, right? I'm not claiming that I could do that. I'm talking about shared suspensions where people use Smoluchowski type equations for a long time. That's basically my claim. But for these type of systems, I can do it. I'm not claiming I can do it for a granular system. I need the underlying dynamics of Lorentz type, or as we'll see tomorrow, kind of master type equation dynamics, Markovian dynamics. Okay, I think the 60 minutes. 15 minutes. Okay. We had a lot of discussion. I actually wanted to sketch. Let's see. Yeah. Okay. I wanted to sketch the derivation of this result very briefly. So what you have to do to derive this fluctuation theorem in this form is that you have to derive two relations involving such a response or a correlation function. And the first thing you do is you solve the Fokker-Planck equation with an additional small perturbation, very much as you do time-dependent perturbation theory in quantum mechanics or whatever. And then you find that the response of any observable taken at a later time with respect to the force applied at the earlier time, T1, that you can express this as a correlation function between this observable and some other observable. Okay, so this is now a non-equilibrium steady-state average. This is the response of this observable with respect to perturbation at some earlier time. And the whole question is, what is this B variable? And if you do what I just described, you solve the Fokker-Planck equation, you split it in an L0 part and a small L1 part, then you find that this B variable, that's now just a variable of x, that this B variable for a Fokker-Planck equation where you write the generator as the sum of an unperturbed generator, which is the nest state, plus this additional operator, which in our case, L1, would just be minus f by dx. That's exactly how the force shows up in this Fokker-Planck equation over there. Okay? And then it turns out that this B of x is nothing but the stationary distribution at times x times this operator divided by 1 of x. And to my knowledge, the first one who has derived such a non-equilibrium steady-state response fluctuation relation was Agarwal in 72. And you find that derivation in Riskin's book on Fokker-Planck equations. So all these claims that there is nothing like a non-equilibrium fluctuation dissipation theorems are nonsense. I mean, there is a mathematical structure which looks very much like this. Okay. So now you take, in this particular case, you take for L1 this perturbation operator. The PS has been defined over there. And when you do that, you find that this B of x is the mu of x, which was introduced, minus the f of x divided by t. Okay. that's piece of information 1, which you need. And you can actually, you don't have to copy that, you find it actually in my EPL with so much back on the FDT. Okay. Now, suppose we had done that in equilibrium. In equilibrium, this nu is 0. So F is just V prime. So we would have, if we applied that to equilibrium, we would have that the response of any observable taken at the later time, force taken at the earlier time, is just A2 V prime of x taken at time 1. This is not the FDT, how you know it. Okay. But it's true. It is. It's true. The second piece of information is, look at this Nonequilibrium equation. X dot is mu times F plus some additional force plus the noise. I'm looking, suppose I change the force a little bit. I can also change the noise a little bit. When I change the force a little bit at some earlier time, or I change the noise a little bit, doesn't make any difference. Which means that this response function, so if I look at A2 at some earlier time, is the same as if I look at how A2 changes if I change the noise at some earlier time, divided by mu. Now you write for this, you write a path integral. And you shift that partial derivative from the observable A to the path weight, which gets you down 1 zeta. So this then becomes mu over 2 d, that's the path weight, for the Nonequilibrium noise, A2 times zeta 1. So you can replace the response with respect to a force by a correlation function of that observable with a noise at some earlier time. Sure. Now what you do now is that, so this is 1 over 2t. You just replace this noise by the Nonequilibrium equation, which is x dot minus df. Okay? So you see that you can. So now we have a response correlation here. So you see that for all practical purposes, this with a factor of 1/2 is equivalent to that. And now you take 2 times this relation, you subtract 1 times this relation, you get on the left-hand side the response function, on the right-hand side you get this. And I've also shown or sketched how you get this useful result, where you do not need to know stationary distribution.
Just I think we have a little notation confusion. So the EF here is now the total force in the nozzle, the capital F in the nozzle equation. The little f is what you add in this linear response about the mass, right? And this is all down in the limit of little f going to 0. Because you do a linear response about the non-equilibrium states.
This is all net yes. Sorry, yes. Thanks for that clarification. Okay. So, message. There is something like a non-equilibrium fluctuation dissipation theorem. It comes in different versions, and it's based on physically transparent quantities. I think I'll answer.
We have still some minutes for more questions.
Yes.
So 2 questions.
Yes.
So does it mean that there is something like an Onsager regression hypothesis about non-equilibrium steady states?
Yes, I think that's what I tried.
And that's independent of the nature of the non-equilibrium steady state?
Well, I need my rules. I need my rules. I need the Fokker-Planck equation. Noise is thermal. I mean, you can do that for master equation dynamics, and then you get expressions which are not particularly transparent, but the formal structure carries over. Yes, please.
There is a non-equilibrium steady state, and you think of all the particles now, they have a certain velocity at the end of the day, and that's not changing in time. So fluctuating around something.
Yes.
So your transformation there was really going to that for each particle, going to that steady state velocity. Is that right? I have missed that.
Well, in a sense, yes. Doing that in phase space.
Okay, and then you're saying, then I have around that velocity fluctuations and this direction.
Yeah. But, we started that, but for the strong statements in this direction, I would really address you to Kravetsky's papers.
What is the meaning of that stochastic entropy?
Okay, good question. If you accept the idea that the heat exchange has a stochastic contribution, that the heat exchange between the system and the environment is fluctuating along a trajectory. If you accept this, I've shown you that if you then accept my definition of a fluctuating system entropy, that if you add both together, you find nice results like this integral theorem, like this detailed fluctuation theorem for finite times. This is a little bit of a formal theorist's answer. And if you want to measure this quantity, you have to measure the stationary distribution and look at the log, right? I cannot measure the system entropy in a calorimetric fashion. But my claim would be that to close this framework, so people accept that work is a stochastic quantity. People accept that the heat exchanged heat is a stochastic quantity. I show you, if you go one step further, if you have a stochastic entropy of the system, this becomes much rounder and much nicer from my perspective. That's why I think it's justified to introduce that. You don't have to agree. That's fine with me. Yes?
If you naively apply the equilibrium FDT
yes.
to the non-equilibrium steady state, do you get anything sensible?
No.
It's just nonsense.
Nonsense. Plain nonsense. Nobody should do that. I have to refer you too many papers anyway. So there was a question over there. No?
Any other questions?
Yeah. I kind of skipped ahead in the notes.
Yes.
To the Hatano and Sasa and
yeah. Oh, yes. Sorry. Yes.
And the housekeeping and stuff. I was just curious if you think these results say anything about possible, like non-equilibrium thermodynamics for steady state. Something practical and reasonable.
Yeah, I think these are first steps. Okay, so as in classical thermodynamics, we discuss transitions between equilibrium states, different equilibrium states, and we have closest relations. Hatano and Sasa have shown that you have some similar concept if you go from oneness to another. I certainly think this is a very valid question, and they have a nice result about that, and we have some variants of that which you would find in that table. But it belongs to this story of non-equilibrium steady states. How useful it is at the end, I don't think we really know that yet. But it's an attractive idea to develop thermodynamics further.
Are there experimental tests of the
Yeah, this is this Trepanier paper. I have quoted here, and we're doing similar things now for less trivial potentials.
Any other questions?
So just thank you.